Hello everyone, this is Mr. Kaviani, and by the end of this video, you should be able to interpret and describe the relationship between a position time graph, a velocity versus time graph, and an acceleration time graph. And you should be able to construct a graph of velocity versus time and acceleration versus time given a position versus time graph. Now, we've already discussed position time graphs, but to discuss velocity time and acceleration time graphs, I'm going to go back to our familiar buggy car example. Recall that the position versus time graph for the buggy car, a car that traveled at a constant velocity, looked something like this, right? We had a positive linear relationship, and because the speed of the buggy car is constant, right? And I know that the slope of this graph, I'm going to write that out, the slope is the speed for this graph. The slope here was a constant value, and the slope was about 46 centimeters per second. That's what we got from our experiment. And so I know the position time graph looks like this. I know the speed, or the velocity in this case, we're going to use them interchangeably because the buggy car travels only in one direction, is constant the entire time. So when I'm thinking about graphing the velocity of the car over time, what might that look like? Take a moment, pause the video, and see if you can predict what the shape of the velocity versus time graph would be for this same buggy car. Okay, now I like to think about it like this. If the position versus time graph, the slope of that graph is the speed of this car, and the slope is constant, that means the speed is the same, or the velocity is the same the entire time. And I know the value is 46 centimeters per second. So our velocity versus time graph's actually going to look something like this. I'll say this is 46 centimeters per second, and at every time, right, it's the same value. So we actually get a flat line for our velocity. What this is saying is that at every point in time, right, all along this time axis, our velocity is just 46 centimeters per second. It doesn't change, basically. Okay. Then if I were to think about the acceleration versus time graph now, well, I know acceleration is a change in my velocity, but my velocity never changes at all. So I know then that my acceleration the entire time must be 0. So I'll show that right here at 0. In other words, the car never accelerates. It travels at a constant speed of 46 centimeters per second the entire time. So what I've just done is I've translated a position time graph into a velocity time graph and an acceleration time graph. And this was a straightforward example. Let's take a look at a slightly more complicated example on the next slide. Now, let's say instead of a buggy car, you're in an actual car stopped at a red light. Once the light turns green, you slam your foot on the gas pedal and your car begins to accelerate at a constant rate. Now, my position time graph looks a little bit different. Pause the video and take a moment to think about this. If the speed is the slope of the position time graph, and my speed is constantly increasing here as I accelerate my car, what would the shape of this graph look like instead? Pause the video and see if you can predict this on your notes. So when I'm stopped at the red light, my speed is 0. So I begin with an initial velocity of 0. So I know that my slope here on this graph will begin at some 0 point. And as a reminder, this represents a slope of 0, right? And a vertical line represents a slope of 1. So anything between a horizontal and a vertical line has a slope value between 0 and 1, essentially. So I'm going to show my curve looking a little bit like this then. I'm going to have some initial very shallow region, but over time my speed increases, so my slope is going to increase and slowly become more and more positive. Again, this is assuming that we're speeding up and we're traveling in the positive direction. So I'm going to show this curve increasing until eventually, right, my slope almost ends up at 1. And so let me show you with blue here what the slope looks like. The tangent line, so if I draw a tangent anywhere on this curve, will indicate the slope value. So the slope here is basically 0. Then as I keep going, right, the blue line shows the tangent line. And then almost there. So this is a little bit like small, positive. This is like medium, positive. This is larger, positive. Again, this is all kind of subjective. And this is, almost 1. essentially. So as I can see, the slope is becoming more and more and more positive, right? The speed is increasing. Now, again, on my velocity versus time graph, I'm going to show that on the velocity versus time graph now. The slope of the position versus time graph, so the slope of this graph of position versus time is the y value of the velocity versus time graph, right? Whatever my slope value is on the position versus time graph, that's my speed. So on my velocity versus time graph, or speed or velocity, I'll show that as the y value, right? Because I'm graphing velocity on the y-axis directly. So I'll show that it starts off, again, at 0, right? I don't have any speed at the beginning. And then I said it becomes, over a little bit of time, slightly positive. And again, we're not going to worry about the exact slope here. Then it becomes more positive, and then even more positive, right? So I'm going to connect those. And this should be fairly linear, right? It's not exactly linear in this example, but I'm traveling with a constant acceleration. I know that. When I put my foot on the gas pedal, I keep it at a steady acceleration. So I know the slope of this graph is actually my acceleration, right? So the slope of my position time graph was velocity or speed. Again, I'll use these words interchangeably here today. So the slope of my velocity time graph actually ends up being my acceleration. So the slope here is my acceleration. Just to prove that, I want to remind everyone that the slope is, again, my change in y or over change in x. That's rise over run. So for this graph, the change in y would be the change in my position over the change in x, which is the time. We'll just show that as time, right? And I know that this is equal to velocity, right? Velocity is defined as my displacement or my change in position over time. So that checks out. For my velocity versus time graph, the change in y over the change in x here is a change in my velocity, again, over time. Well, I know that that is the definition of acceleration, so I can check myself there as well. Now, if my position time graph looks like a curve upwards, my velocity time graph then is a positive linear relationship. The slope of this line, hopefully we agree, is constant, right? I have a constant slope. So I'm going to have on my acceleration time graph then, the slope here will be the y value here. But it's just one value, right? This slope doesn't change. So whatever the slope is of this velocity time graph will be the y value on my acceleration time graph. I'll just show that here. Again, I'm not worrying about the exact numbers right now. I just know that it'll be some positive acceleration. And it will be constant the entire time, okay? Now, it's important to know that no matter what, for this class, if you have acceleration, right, your position time graph will be some sort of quadratic or some sort of parabola, right? Your velocity time graph will be some sort of linear relationship. And your acceleration time graph in this class will always be a flat line. Why? Because we will never deal with an acceleration that is not constant. In a sense, we will never deal with an acceleration that changes. At the most, we will have some constant acceleration, like we show here, right? So this velocity time graph will either always be linear or flat. It'll be linear if we have acceleration, and it'll be flat if acceleration is equal to 0, like we saw in the previous example.